This is A-level further maths, further pure 1, specimen paper question 2. This question involves vectors, and it looks like a relatively quick question. There are just 4 marks available. They've given us 3 vectors, A, B, and C. So the first thing I'm going to do is write them in column form so that we can see what we're dealing with. B is 3 minus 1, 1. And C is 2, 1, minus 1. You might be forgiven for thinking when you read A equals I plus J that A is just a 2-dimensional vector, but if we're dealing with vectors in the context of 3 dimensions, then we're going to assume that it's a 3-dimensional vector that just doesn't have a k component, so its k component is 0. Now, there are 2 things we've been asked to find here. One is the area of a triangle enclosed by the vectors A and B. OBC means the triangle that goes from the origin to B and then to C and then back to O again. So you might want to sketch yourself a quick picture so that you can visualize what's going on. If we've got the origin and we've got the point B and we've got the point C, we're just looking for the area of a triangle that will go between them. So from O to B, from B to C, and from C back to O again. Now, it may be that you don't need to draw this out to see what's going on, but sometimes if you're a little stuck and you need to buy yourself some thinking time, a little bit of a diagram can be helpful. It might be that you've forgotten some of your vector results, but you remember some results involving triangles. So for instance, in this particular case, knowing a bit of A-level maths will be sufficient for you to calculate the area of this triangle, and it should be allowable, although it will take you longer than the more efficient methods, to calculate using, let's say, half AB sine C. But perhaps even if that's all you remember, bear in mind the A and the B in this equation are not the same as the A and the B here, which I should make bold because these are vectors. Even if this is all you remember, you might have something triggered in your memory by the fact that you've got sine of an angle, making you think, well, this may have something to do with the cross product. And if that's what you were thinking, then you are absolutely correct. The cross product is by far the quickest way to deal with this question. And in fact, it will also allow us to deal with the second part. So if you can work with the cross product, that's going to be better than relying on some other formula that doesn't use vectors. For the cross product, we need to pick a couple of vectors that represent the sides of this triangle. And in this case, it seems to make the most sense to choose the ones that we already have information about. So we've got the vector OB, which goes from O to B. We're going to find the cross product of that with the vector OC, which goes from O to C. The other thing we need to be aware of is that when we calculate this area using the cross product, it does not give us the area of a triangle. What it in fact gives us is, based on the definition of the cross product, if we do A times B, where A and B are vectors, what we construct for ourselves is a vector to start with, so a vector n, which is a normal vector, but then the size of that vector is determined by something involving sine theta. So we'll call that n hat to give us the unit vector in the direction of a normal, a vector which is perpendicular to A and B, but then the size of the vector is given by the size of the vector A multiplied by the size of the vector B, multiplied by sine of the angle in between. And if you remember this fundamental definition, in the same way that if you had A dot B, we've got a similar-ish definition for that one. It's going to be mod A, mod B, cos theta. And in this case, just a scalar, so there's nothing else going on. In the case of the cross product, we multiply that by the unit normal vector. So we end up with a vector whose size is equal to mod A mod B sine theta. You can start to see the link here between half AB sine C and the cross product. But that means that if you want the area of a parallelogram, all you need to do is find the cross product. If, on the other hand, you want the area of a triangle, we use the fact that the triangle is half of the parallelogram. The only other thing to mention at this point is that technically, because area is never negative, you may need to positivize the result. it's possible that when you take the cross product, depending on the direction you go, you might end up with a negative area. And since we just care about the size, the actual area itself, rather than the signed area, we would put modulus signs around. That's enough. All we need to do now is compute this. And the quickest way to do this is to write down the vectors you're going to be taking the cross product of. We've got OB 3 minus 1 1 and OC 2 1 minus 1, and then let the calculator do the heavy lifting for you. So the calculator has a vector mode. Vector mode is number 5. We can define our vectors. So vector A can be 3 minus 1 1, and vector B, define vector B, also a 3-dimensional vector, and this one's going to be 2 1 minus 1. Now, maybe it would have been better to define these as B and C, but I'm only going to use them the once. I've defined them as the first two vectors in there, and now I'm going to do some vector calculation by selecting the first of my vectors, vector A, and finding the cross product with option number 4, vector B. This is the cross product 0, 5, 5. So I just need to find the size of the vector 0, 5, 5 and multiply it by a half. Fortunately, this is pretty quick to do. If you want to use the calculator, then you can. You'll need 5 squared plus 5 squared plus 0 squared if you really want. That will give you the square of the size. So the square root of that, which is going to come out to be 5 root 2. We then just need to multiply by a half. So our final answer is 5 over 2 root 2, or 5 root 2 over 2 if you prefer. The precise way you write that doesn't really matter as long as it is the exact value. We don't want any approximate values in here. We want the area of the triangle. So that's the first part. That's part A. To get part B, we want to make this as quick and efficient as we can. So we're going to make use of the scalar triple product. So in part B, we use the fact that the volume of a tetrahedron is related to the volume of a parallelepiped, but it's a sixth of the size. In much the same way that the area of the triangle was half of the area of the parallelogram, we're going to use volume of a tetrahedron is a sixth of whatever the formula will be for a parallelepiped. Now, a parallelepiped, strange name though it is not too crazy a shape. It's what you get if you relax the angle requirements on a cuboid. So you allow the base to no longer have to be a rectangle, but potentially a parallelogram. And you allow the various other sides to do what they want as well. Now, it doesn't mean that anything goes. The definition of the word involves the word parallel. All the faces are parallel to the opposite face. So the parallelogram base is parallel to the parallelogram top. And same with the front and the back and the left and the right. So there are really only 3 different faces there. And in fact, there's only really 3 different edges that we need to worry about. All of the vectors that travel from the front to the back are parallel and the same length. In other words, they're the same vector. And those 3 vectors, if we call them P, Q, and R, for instance, we can use to find what's called the scalar triple product. P dotted with Q cross R. The only other thing we need to be careful of here is that, as before, potentially this will come out as a negative, so we need to put modulus signs around it. But P, Q, and R, the only requirement on these is that they are non-planar vectors. If you find 3 non-planar vectors, preferably just sprouting out from one corner of your parallelogram, that's the easiest way to think of it, then you can find the volume of your parallelepiped by doing the scalar triple product. And if you want the volume of a tetrahedron, you just have a sixth of that. Essentially, because things have been scaled down in all the different directions, you could fit 6 such tetrahedra inside one parallelepiped. We just need those vectors. And since we're looking at the tetrahedron OABC, we can think of the diagram we've already got. Now imagine another point, the point A, but not sitting on the same plane. So it's not on the page or not on the screen. It's somewhere just above the screen, perhaps, sitting up there, giving us a tetrahedron. We're going to use the vector from O to A as well as the OB and OC vectors as our three non-parallel or non-coplanar vectors. So we want a sixth of the size of, we're going to use as our vectors the vector OA and then the vectors OB and OC. The reason I'm putting them in this order is that we've actually calculated the cross product of OB and OC already. And this will make our life a whole lot easier when we get to this stage. The vector OA we've been given in the question. That's the vector 1, 1, 0. That's the position vector of the point that they're describing there. We want to dot that with the cross product that we've already found. We did the cross product of OB and OC. We got 0.55. So we can take that and use it for this next part. Now you can use the calculator to compute dot products, but it's really overkill. All we need to do here is 1 times nothing, 1 times 5, nothing times 5, and add them all together. And since the size of 5 is 5, we get an answer of 5/6. That will be the volume of the tetrahedron. If you want to calculate roughly what the size of these things are, 5 over 2 times root 2. Root 2 is about 1.4. If you halve it, you get 0.7. If you multiply that by 5, you get about 3.5. The volume we're ending up with is 0.8-ish. And so if you're comparing them, you might be surprised that a tetrahedron, which has this as its base, has such a small volume. But in fact, because it shrinks to a point, it's going to have a volume which is a third of the volume of the containing triangular prism. So unless the point A is a long way away from the OBC base, we're going to have quite a small volume here. Let's have a quick check at the mark scheme and see where the marks are being awarded, what methods they would expect. First of all here, they're showing the bare minimum, so you may write more, but you do not need to write more than this. If you've recognized that you can get the area of the triangle by using the cross product, then apply the cross product, get an answer of 0.55, and then find half of the size of that vector. You get 5 over 2 root 2, your job is done. In the second part, making use of the scalar triple product, and again, they've used the more efficient method here. There's nothing wrong with doing B dot A cross C, for instance, or something else, putting those vectors in a different order. But it makes the most sense to use a more efficient version, so we're going to make use of the cross product we had previously. All we do is what they've done here, take the dot product with the vector A, calculate the result, and then multiply the size of that by 1/6.